quick and dirty Python, or rather slow and dirty Python. And why is that? Well, Python is an interpreted language. What does it mean? Every single line of code is being read and then it gets interpreted and executed. So you can think of it as you type something, or maybe let's actually look at an example, it will be a bit easier to visualize it. So Python reads every line of this file. So it reads def is prime and int bool. Then it decides what it is and then reads the next line. Then reads it if n is equal to 2, decides what does it mean, and then goes to next. And it generates this, I don't know what it does. Actually, interpreted language are quite interesting to read, maybe read more on the topic, delve deeper into how they work, but maybe that's for another video, I do not promise. On the other hand, there are compiled languages. So let's maybe talk about Rust, for example. Rust code, let's maybe look at this. Rust code, you write a program and then you pass it to a compiler, and then compiler takes it and does all the interpretation and then stores this code somewhere. So that's the main difference, that Python is interpreted on the fly, and you could say that compiled languages are interpreted beforehand and then are put as a separate program. So for example, libpynumcheck is like this. This is the code. Literally, this is all the code that it gets generated. It's of course binary, so only computer can read it. So you can think, or you can wonder why, for example, Python is better or worse, but I hate Python. I will say it at least once every video. Okay, what this video is about. I have found a very interesting library for Rust, which is py03. If you actually look at the dependencies, it's py03. And I can create Python libraries in Rust. What does it mean? That I don't need to program an entire thing in Python. I can just program an interface. So this task is exactly the number checker task from a previous video. And here I have 10,000 numbers, so that lacks my computer. But I have here the code, and the code is the same, so I have explained it in a previous video. And then we have numcheck2, which is the same but in Rust. So what it does, we have a run function. We do not have the functions which check. We have a module, pynumcheck. This module is implemented in Rust and gets read by Python, and the code gets executed. So we still have some Python interpretations of formatting the output, but the calculations themselves are done by Rust. And then we have 10,000 random numbers, which then for every number in n, we run this program. So maybe let's talk about the differences. How I check for a number is prime. I did not use a library because I want to make this all fair. So I implemented a prime sieve. So 2 is prime, so I return true. If it's even or 1, then it's not prime. And then I check for if it's odd, then I start from 3. And for every number from 3, so here for every number from 3 up to 2, so from every number from 3 incrementing by 2 up to the square root of n, rounded up, so like here, I check if it has any divisors. Why rounded up? Well, let's for example take 49. It is not prime but it has very simple prime factors. It's 7 squared. So I don't actually need to check for lower numbers. For example, I don't need to check for 8 because there is no way to multiply 8. Well, there is no other prime factorizations. Prime factorizations are unique, and the least it can be a prime squared. That's why you search to a square root of n, and you skip by 2 because you skip even numbers. You don't need to look at even numbers. And then if I find a divisor, then it's definitely not prime, so I can return. And if all the tests fail, I return true because the number is prime. Then for even, it's simple casting n mod 2 to boolean and doing a not because n mod 2 is 0, so it's false, but I return not, so it's true if it's even. And then solve quadratic is the same as previously, so I use cmath square root to get the square root. I use A, B, and C, and D, use the quadratic formula, do some formatting. This was explained in the previous video, and with the difference that I return a string, which is a formatted string of the results as a tuple. So imagine you print a tuple. So that's how I print the tuple, and I return it. And then in the run function, we just perform all the checks. I do check for valid input, I check for evenness, I check for primeness, and I solve the quadratic equation. That's it. Then let's see how it's implemented in Rust. So py03, you need to define the function names as py function, like this. Okay. So maybe we'll do this with a module instead, like so. Okay, so I define Python functions, which will be available in Python. I don't know about the PyResult really. I didn't delve into the py03 too much, but it's basically you here define the name, and I think usize is equivalent to Python integer or whatever. Because Rust has concrete types, and so this also informs Python about the types you can put into these functions. Otherwise, there will be an error. So probably PyResult is some kind of error for the types, or I don't know. Then even checks are very easy. So in Rust, this will be casted. This will be casted to true as a bool and will be returned. Then we have isPrime. We have a prime checking function, which is the same as in Python, although here you have brackets, so you see what is going on inside the for loops instead of what we have here, where it's just some text. Here it's more structured. But I also had to implement a square root function just for this task, because in Python you can easily cast between types. This is a thing with Rust, that Rust has very concrete types and doesn't let you do things which would be potentially unsafe, even if you want this. So in this regard, I think C would be a better choice, because it would be also faster. This ceiling square root function slows Python down, slows Rust down. But maybe it's for a good reason, because Rust wasn't really made to be faster than C, it was made to be better than C. Anyway, we have we have some Rust type juggling, so we have to first interpret it, cast the n to a square root, then take the ceiling, so round it up, and then return it back as an integer. Then the prime checking is the same. If n is equal to 2, we return true. If n is even or n is 1, we return false because it's not prime. And then we start from 3 to the square root of n, and we step by 2. And then if we find a divisor, we return that it's not prime. and otherwise we leave a tail expression which is true, so it will be the return value here. So that's how prime works. Let's talk about quadratic formula. So for this I had to implement a complex number type to Rust. So I do ABC, then a discriminant, that's still simple. And then the first stairs start with discriminant, the square root of the discriminant. What's the problem? What if you get a negative discriminant? Well, you just put it as a pure imaginary number, because that's actually the upside. Well, the reason why I even bothered to do this, that I don't get complex roots. I just get a root of a negative number, which is purely imaginary. What do I mean? Let's look at the complex structure. So here I have a complex structure. It has a real part and imaginary part. I could have even put it as private fields, but whatever. Then I implement the square root function. So what it does? Normally, so let's start from else, it gives a complex number from a float, 64-bit float. So it takes a square root of the float because it's positive or 0, and the imaginary part is 0 from a positive square root. If it's negative, then we take a square root times the complex unit times the imaginary unit. So this minus here is because the square root cannot be taken from a negative number. So we just negate the negative number to get a positive one. We take a square root and we store it as an imaginary part. And we only care about the upper half of the Cartesian of the complex plane, because they are perfectly mirrored in the complex numbers, and for the task of solving quadratic equations you do not need an entire complex plane, because you always get a symmetrical root. One is above and the other one is below. So that's how the square root is programmed. And if we come back to here, we take the square root and then we get the first root and the second with plus or minus. Here also I had to clone the discriminant because it gets moved because of how the add function is defined. But I will talk about operator overloading in a moment. And then I had to also implement a division. I didn't implement the division operator because I couldn't find how to divide a complex by a float. I don't know even if it is possible to do this in Rust. I didn't really do a lot of research, but I divided by 2 times a. It's that simple. And because it's a method defined on complex, it actually has a syntax similar to division. Also, I have a from, because I have implemented a trait from float to complex, so I can use this to construct a complex number from a float, and I do this by just setting the real part to the float and the imaginary to 0. Okay, let's look more at the implementation of complex. So division is simple because I divide it by a float, so I divide both the real part and the imaginary part. I also copy. No need to do this really. I could take a mutable self, but I don't want to worry about anything, so I implemented it like this. Then you have an add trait, and it allows for overloading the plus operator. So it's very easy. We add the real parts and the imaginary parts. Even for this program, I could have omitted the imaginary parts because I do not. Oh no, sorry, I had to do this. No topic. So then we also have subtraction. I copied add, changed here sub and put a minus here. It's the same. And then I put a format so that I could display it. Because in Python here I had to format this as a tuple, and I had this code. And in Rust I just did the same. It's the same code in Rust, but I return a full result and I use the write macro. Interesting thing to note, here I had to explicitly cast it to an integer if the fractional part is 0, so it's a bit different than in Python. And here with the minus is by default if the number is negative, so I don't need a minus, and here I need a plus. So there's another difference. And then I have the from trait, so as you can see, if I give it a float, it will just put the float as a real part, the imaginary part will be 0. And so that's the implementation of quadratic, and then I format it just like in Python, R1 and R2. Okay, now with this explained, let's talk about numcheck 2, which is this. So I import pynumcheck, this is the name of the Python module that I compile with Rust. And then I have the same run function, which just uses the functions from the module. Here is even, then is prime, and then solve quadratic. So we can, there is also the run set script, fully ChatGPT. I just added the is prime function here because, well, ChatGPT wanted SymPy, but I do not want bloatware on my computer. And so I printed the list. I could have maybe changed it to be what? I could have changed it to be into a file, and then I would read those numbers from a file, but this is the random, these are the results from the last test, but this is the list, so if you want you can read it. So it's time I think to run numcheck 1 and 2. And so now let's measure time Python numcheck. So let's measure the time it takes for Python to execute. And it's 284 milliseconds. And numcheck 2, it's 289. So this one was in Rust. But let's actually test it. Maturin develop release. Let's recompile it. See, it needed a recompile. Okay, so now let's test both versions. So you have numcheck, so the Python one, 266 milliseconds, and numcheck 2, 259 milliseconds. So very close on 10,000 numbers. So why is that? Well, I actually don't know. Maybe because my computer is a bit more loaded, or the values are cached somewhere, because I've run this test before and I got these values. So Rust was 60 milliseconds faster. Let's actually maybe run it again. 200, well, around 260, and then Python 280, 300. 280. So Python, as you can see, is consistently slower, but by not much. Why? Well, because we do very little operations, and the libraries are actually very optimized. Something which I do not have at this moment, which my Rust code isn't very optimized. Even if I have compiled it for the release, I probably could tweak some flags, maybe use something else. This is one which you could say maybe an advantage of Python, that it's even everywhere on every platform. You don't need a lot of tools because it's never optimized. That's why I hate it, but that's maybe the reason why it's so used, that you don't need any tools for it. There is no way to optimize it anyway. With Rust, I probably could do some obstacles. I could jump over some obstacles, do some magic, and optimize it. but I think there is no need to. But I have shown that Rust is faster, and that's because it's compiled. So the code is taken and the computer already knows what to do ahead of time, so it just executes it. In Python, my computer has to think, what does it mean to define a function? So then it defines a function. But as you can see, it's not that slower on 10,000 numbers, but maybe maybe it scales. So actually let's make a test and let's actually run the same thing again in the same numbers. I could have copied. So let's actually run it twice, and let's now see. So the Python one, see, 550, and numcheck 2, 515. So it scales with size. The more you do, the slower Python gets. I think it would be more exponential than in Rust, where it would be linear. Everything would depend on the code you wrote, and in Python it depends on the interpreter. So this is another thing. In Python, not a lot depends on you, whereas in compiled languages like C or Rust, you are in control of the speed of your program. It will run as fast as possible, but if you program it to be slow, it will be slow. And I think that will be it for this interesting comparison and an interesting piece of software, which is PyO3, which I will definitely be using in the future because I hate Python and so I want to write my code in Rust. And well, that would be it. So bye.